Ever been comparing two things that, well, look the same on the surface? Like, imagine two investment plans,
Okay.
both promising, say, an average 8% return, but one feels like a total roller coaster, you know? Huge ups, huge downs,
Right. High volatility.
while the other's just steady. Or think about picking a restaurant, maybe based on an average star rating.
Mm-hmm. Happens all the time.
One might have really consistent 4-star reviews, solid, but another, it's a mix, right? 5-star raves and then these 1-star disasters.
Yeah, that average hides a lot.
Okay, let's unpack this. Because you're the kind of person listening now who wants to really get what's going on,
Mm-hmm.
to understand the nuances behind the numbers, but maybe without needing a PhD in stats.
Right. You want the real story.
And that's exactly what we're diving into today.
It's fascinating, actually, because those everyday examples you mentioned,
Mm-hmm.
they perfectly show why just knowing the average, well, is often not enough information.
Right.
It's like knowing the average temperature in a city. Doesn't tell you about the boiling summers or the freezing winters.
Good analogy.
We need to understand the spread of the data, how much the individual points vary. That's really the heart of data dispersion.
Exactly. So for this deep dive, we're tackling statistical measures of data dispersion. Think of dispersion as like the variability, the scattering of values in a data set. It shows us how much our individual pieces of info differ from each other, or maybe from a central point like the average.
Yeah, how spread out things are.
We've got some great excerpts from a resource also called Statistical Measures of Data Dispersion. It lays out the core ideas.
And it touches on how these concepts are used today, right?
Yeah,
In places like healthcare, machine learning.
exactly. It's really relevant stuff.
And if you think about the bigger picture, understanding this dispersion, this spread, it's just absolutely key.
Why is that?
Well, it lets you judge the consistency of the data, right?
Mhm.
The reliability. How predictable is it? It moves us way beyond just simple summaries.
Okay.
And it empowers you, the listener, to make much more informed decisions based on that data.
So our mission today is pretty straightforward. We want to equip you with a practical grasp of how to interpret this, spread this dispersion of data. We want to show you why it has real-world impact. Basically, turn you into someone who can quickly understand the true story the data is telling.
It's like a shortcut to being properly well-informed on this.
Your shortcut. So where do we kick things off? Where do we begin this exploration?
Well, a logical starting point, I think, is the simplest way to get a feel for the spread,
Yeah.
and that's the range.
Okay, the range. Sounds pretty basic. What exactly is it and why start there?
The range is literally just the difference between the highest value and the lowest value in your data set. Simple as that.
Okay. Max minus min.
Exactly. It gives you an immediate, though, pretty rough idea of how spread out the data actually is. It's super easy to calculate,
Right.
which makes it handy for, quick initial checks or in areas like basic quality control. Think of it as a quick alarm bell for potential variability.
I sense a but coming.
Well, yeah. Remember, a single loud ring, like one outlier, can sometimes mask what's happening in the rest of the data. It doesn't tell the whole story.
Got it. So how do we actually figure out the range? Give us the mathematical lowdown, but keep it simple.
The formula couldn't be simpler, really. It's just R, X max, X min.
Maximum value minus minimum value.
That's it.
Simple enough. Let's try a quick practice run then. Imagine I've got some test scores. 82, 74, 91, 65, and 78.
Okay.
What's the range in this case?
Okay, so first you find the highest score. That's 91.
Right.
Then the lowest, which is 65.
Got it.
Then you just subtract 91 minus 65. That gives us a range of 26.
26 points.
Yep. And you could also express it as an interval, like 65, 91. That shows the whole span.
Okay, that makes sense. Let's do one more. Say we're tracking daily high temperatures, Celsius, over a week.
Okay.
And we get 20, 22, 19, 25, 18, 23, and 21. What does the range tell us here?
All right, so the highest temp is 25 degrees C, and the lowest is 18.
Right.
So the range is 25 minus 18, which is 7 degrees.
Only 7.
Yeah, a small range like that suggests the temperatures were, well, pretty consistent that week, stable.
So the range gives us a really quick, top-level view of the spread, but I'm guessing it doesn't paint the full picture. What are the downsides?
You're absolutely right. It doesn't. The main issue is that the range is very sensitive to outliers.
Outliers. Extreme values.
Exactly. Let's go back to our test scores, 82, 74, 91, 65, 78. The range was 26.
Right.
Now, what if one student suddenly aced it and got 100? Our data set becomes 82, 74, 91, 65, 78, 100.
Okay.
Now, the max is 100. The min is still 65. The range jumps to 100 minus 65, which is 35.
Wow, just from one score.
Just from one score. That single extreme value really skews our understanding of the typical variability in the class.
It's like that one crazy stock in your portfolio making the whole thing look riskier than it is.
Perfect analogy.
Yeah.
It can make the overall range of returns look huge, even if most stocks are pretty stable.
Okay, that's a big jump. So one unusual data point can really throw it off. What else? Any other limitations?
Well, it also doesn't tell us anything about how the data is distributed between those two extremes.
Ah, right, the middle ground.
Yeah, you could have two data sets with the exact same range, but completely different patterns inside that range. One could be clustered in the middle. The other could have two separate clumps. The range wouldn't show that.
Okay.
And finally, it's not what statisticians call robust, meaning it's easily affected by small changes, especially if those changes involve the min or max values.
So are there better, maybe more robust ways to look at spread that fix these issues?
Yes, definitely. One really important alternative is the interquartile range, the IQR.
IQR.
Yeah, it focuses just on the middle 50% of the data, so it's much less bothered by those extreme outliers.
Ah, that sounds useful.
And, in the modern world of data science, tools like Python's NumPy library make calculating this simple range incredibly easy. Just a simple command.
Like np.max data, np.min data.
Exactly that. And this basic range calculation is still used, actually, in big data preprocessing for something called min-max scaling. Yeah, transforming all your data so it fits within a specific range, usually 0 to 1. Helps algorithms work better sometimes.
I see. So, despite its limits, are there still situations today where the simple range is genuinely valuable?
Oh, absolutely. Think about healthcare.
Mm-hmm.
Monitoring the range of a patient's vital signs like their blood pressure over a short time.
Mm-hmm.
A sudden widening of that range could be an immediate red flag. Might signal a problem brewing.
Quick check, yeah.
And it's used in quality control for medical devices too, like
Yeah.
an infusion pump delivering medicine. You'd want the range of dosages it delivers to be extremely narrow
Definitely.
for safety and consistency. So range has its place.
Okay, the range fast, maybe a bit misleading sometimes, useful for quick checks, but definitely has limitations. So what's the next step then in getting a more complete understanding of how our data is scattered?
Well, the next logical step is to look at frequency distributions.
Frequency distribution.
Yeah, this moves us beyond just the highest and lowest points. It helps us actually visualize the shape of our data.
Okay.
It's like moving from just knowing the highest and lowest peaks in a mountain range to actually seeing all the hills and valleys in between.
Frequency distributions. That sounds
Yeah.
like it's about counting things, like how often different values show up.
Precisely. That's
Yeah.
exactly it. A frequency distribution organizes your data to show how frequently each unique value, or maybe a range of values, occurs within the data set.
And why is that helpful?
It helps us see patterns, identify the most common values, understand the overall shape of the distribution. Is everything clustered around one point, or is it more spread out? Is it symmetrical?
Gotcha. So what are the different ways we can actually create these frequency distributions? Are there different types?
Yeah, there are a few main types. First, the most basic is a simple frequency distribution.
Simple frequency.
This is where you literally just list each unique value in your data set and count how many times each one appears. Simple count.
Right.
So for instance, if we have the ages of, say, 6 people in a small study, 25, 30, 25, 40, 30, 25, our simple frequency distribution would just show age 25 appears 3 times, age 30 appears 2 times, age 40 appears once.
Okay, I get that. Dead simple. You can immediately see 25 as the most common age there.
Exactly. And from that simple table, we can also calculate something called the relative frequency.
Relative frequency.
Yeah, that's just the proportion or percentage of times each value occurs compared to the total number of observations.
So in that age example.
For age 25, it appeared 3 times out of 6 total participants. So the relative frequency is 3 divided by 6, which is 0.5.
Or 50%.
Or 50%, exactly. Tells you half the group was 25.
Got it. Now, what about when we're dealing with data that has a really wide range of values, like tons of different numbers? Listing every single one might get messy.
Right. It could become impractical or just too long to be useful. That's where grouped frequency distributions come in.
Grouped.
When the data has a broad spread or it's continuous, we group it into intervals or classes. We define bins of a certain width. Yeah, ranges. Like if we had test scores from, say, 60 up to 100. Instead of listing every score, We might create groups like 60, 69, 70, 79, 80, 89, 90, 100.
Ah, okay, so you lose a bit of detail.
You do lose a bit of the granularity, yes.
But it makes the data more manageable, helps you see the overall trends.
Exactly. Then we just count how many scores fall into each of these bins or ranges.
So instead of seeing exactly how many people scored, say, a 78, we see how many scored somewhere in the 70s range.
Precisely. And with these group distributions, we can also calculate cumulative frequency.
Cumulative, like adding up as you go.
Exactly. It's the running total of frequencies as you move up through the intervals. So it helps answer questions like, how many students scored 79 or below? Or what percentage scored less than 90?
Ah, okay. You sum the counts in the current bin and all the bins below it.
Yep. And you can do the same for relative frequency, giving you cumulative relative frequency. Shows the proportion of data up to a certain point.
So it gives us a sense of where different percentages of the data fall within our grouped intervals, like percentiles.
Exactly. For example, looking back at those test scores grouped into intervals, the cumulative frequency might tell us that, say, 6 out of 10 scores were 84 or below. That's super useful for understanding percentiles and where specific values rank.
Now, how do we decide on the width of these bins and how many bins to have? Is there a rule or is it just guesswork?
It's not pure guesswork, but there's definitely some judgment involved. Generally, you want enough bins to show the shape, but not so many that it gets noisy again.
Okay.
A common guideline is to aim for somewhere between 5 and maybe 15 intervals, depending on the dataset size. There's even a formula, Sturgis formula, that gives a suggestion based on the number of data points, n. It's something like k equals 1 plus log base 2 of n.
Whoa, okay. A formula.
Yeah, but it's just a suggestion. Often you try a couple of different bin widths to see what reveals the most meaningful pattern without hiding too much detail. You want the groups to make practical sense too.
This all sounds like it could be pretty time-consuming to do by hand, especially with a big data set. How have modern tools changed things?
Oh, completely. It's night and day. Modern statistical software or libraries in programming languages like Python, they've totally revolutionized this.
How so?
Well, take Python's pandas library. It has functions like value counts for simple frequencies and cut to create those grouped bins automatically, just a couple of lines of code.
Nice.
And visualizing these distributions is just as easy. You can create histograms, those bar charts, showing the frequency in each bin using libraries like Matplotlib or Seaborn.
So you can actually see the shape instantly.
Instantly. A quick bit of code like data.hist or maybe data.plot kind of can give you that visual representation straight away.
That's fantastic. Being able to see the distribution visually must make a huge difference in actually understanding the data rather than just looking at tables of numbers.
It really does. A picture is worth 1,000 numbers here sometimes. And these tools are used everywhere. Well, in education, analyzing patterns of test scores, like we discussed. In healthcare, you might use them to monitor patient wait times, see how they're distributed, or look at the frequency of different diagnoses.
Wait times, I can see that. You'd want to know if most people wait a short time or if there's a long tail of people waiting ages.
Exactly. Even in finance, studying the frequency of different levels of stock price changes the volatility. Frequency distributions help understand that.
So from understanding student performance to managing hospital queues to analyzing financial markets, frequency distributions, give us a really valuable way to see the spread and, importantly, the shape of our data.
Yeah, it's like getting a visual fingerprint of the data set, much richer than just the range.
Okay.
But to really quantify that spread in a more precise mathematical way, we need to move on. We need to delve into standard deviation and variance.
Standard deviation and variance. Okay, these feel like the big ones, the real workhorses when it comes to measuring spread, right? You hear these terms all the time.
They really are fundamental, yes.
Yeah. So what exactly do they tell us that the range and frequency distributions don't?
Well, at their core, standard deviation and variance quantify the average amount that individual data points deviate or differ from the mean, the average of the data set.
The average difference from the average.
Essentially, yes. Variance is technically the average of the squared differences from the mean.
Squared differences.
We'll get to y in a sec. And standard deviation is simply the square root of that variance. It brings the measure back into the original units of the data.
Okay.
So think of standard deviation as like the typical or average wobble of your data points around the central average value. It gives you a feel for how typical or unusual any single data point might be.
Why do we have to square the differences when we calculate the variance? That seems a bit weird. Why not just average the differences themselves?
That's a really great question. Squaring serves a couple of crucial purposes. First, some data points are below the mean, giving negative differences, and some are above, giving positive differences. If you just average these, they tend to cancel each other out, right? You might get an average difference close to zero even if there's a lot of spread.
Ah, okay. The negatives and positives would balance out.
Exactly. Squaring makes all the differences positive, so they accumulate instead of canceling.
Got it. And the second reason?
Second, squaring gives more weight to large deviations. A point far from the mean contributes much more to the variance than a point close to the mean. This reflects the impact of those bigger variations on the overall spread.
So it emphasizes the outliers more.
It emphasizes larger deviations more, yes. So variance is like an amplified measure of spread. Taking the square root to get the standard deviation then brings it back to the original scale of your data, making it easier to interpret directly.
Okay, that makes sense. So how do we actually calculate these? Can we walk through a simple example? Numbers always help me.
Sure. Let's use a really simple data set. 4, 5, 6, 7, 8. Nice and easy.
Okay. 4, 5, 6, 7, 8.
Step 1. Calculate the mean, the average. So 4 plus 5 plus 6 plus 7 plus 8 divided by 5.
That's 30 divided by 5, which is 6. So the mean is 6.
Perfect. Mean is 6. Step 2. Calculate the deviation of each data point from that mean.
Okay, so 4 minus 6 is minus 2, 5 minus 6 is minus 1, 6 minus 6 is 0, 0.7 minus 6 is 1, and 8 minus 6 is 2.
Exactly. So our deviations are net is 2, minus 1, 0, 1, 2. Notice how they sum to 0.
Yeah. Negative 2 and minus 1 cancel out 1 and 2. That's why you square them.
Precisely. Step 3. Square each of those deviations.
Okay. Minus 2 squared is 4, minus 1 squared is 1, 0 squared is 0, 0.1 squared is 1, and 2 squared is 4. So we have 4, 1, 0, 1, 4.
Excellent. Step 4. Calculate the variance. This is where we average those squared deviations. Now there's a slight catch here.
Oh.
Are we treating this data set as the entire population we care about, or is it just a sample from a larger population?
Let's say it's a sample. That seems more common.
Okay, if it's a sample, we sum the square deviations. 4 plus 1 plus 0 plus 1 plus 4 plus 4, 10.
Right, sum is 10.
Then, instead of dividing by the total number of data points, n5, we divide by n minus 1. So 5 minus 1 minus 4.
Okay, divide by 4, y, n1.
It's called Bessel's correction. Basically, dividing by n1 gives a slightly larger variance, which turns out to be a better, unbiased estimate of the true population variance when you're working with just a sample. It's a technical adjustment.
Okay, trust you on that one. So 10 divided by 4 is 2.5. That's the sample variance.
That's the sample variance squared. Yep, 2.5.
And then the standard deviation is just the square root of that.
Exactly. Step 5. Take the square root of the variance. The square root of 2.5 is approximately 1.58.
1.58.
So the sample standard deviation S is about 1.58. This means that, on average, each data point in our sample deviates from the sample mean of 6 by about 1.58 units.
Okay, that nails it down. Now, I often hear standard deviation mentioned alongside the normal distribution, that classic bell curve shape. How do they connect?
That connection is absolutely fundamental in statistics. In a normal distribution, the standard deviation dictates the shape of the bell curve. A small standard deviation means the data points are tightly clustered around the mean, so the bell curve will be narrow and tall.
Like a steep hill.
Exactly. Conversely, a large standard deviation means the data is more spread out, more dispersed, so the bell curve will be wider and flatter.
More like a gentle mound.
Right. And there's a key rule of thumb for normal distributions called the empirical rule, or the 68-95-99.7 rule.
Okay.
It states that, roughly, 68.2% of the data falls within plus or minus 1 standard deviation from the mean.
Okay, about 2/3.
About 95.4% falls within 2 standard deviations.
Most of it.
And about 99.7%, almost everything falls within 3 standard deviations of the mean.
Wow. That's super useful for getting a feel for where most values lie if you know the mean and standard deviation and assume it's roughly normal.
Absolutely. It provides a quick way to understand the spread and identify potentially unusual values, those beyond 2 or 3 standard deviations.
What about skewness? Does a skewed distribution mess this up? How does skewness relate?
Good question. Skewness refers to the asymmetry of a distribution. Is it lopsided?
Right.
A negatively skewed distribution has a long tail stretching out to the left, meaning some unusually low values are pulling the mean down.
Okay.
A positively skewed distribution has a long tail to the right, some unusually high values pulling the mean up.
And the bell curve is symmetrical, right?
The perfect normal distribution is symmetrical, yes. In that case, the mean, median, the middle value, and mode, the most frequent value, are all roughly the same, right at the peak.
But in skewed distributions.
They tend to pull apart. In positive skew, the mean gets pulled higher than the median. In negative skew, it gets pulled lower. Now, standard deviation still measures the overall spread, even in skewed data. A high standard deviation just means more spread, whether it's symmetrical spread or lopsided spread.
So a high standard deviation doesn't automatically mean the data is skewed. It just means it's more variable, regardless of the shape.
It's exactly right. Standard deviation quantifies the amount of variability, while skewness describes the shape or asymmetry of that variability.
Yeah.
You can have wide symmetrical data or narrow skewed data.
Got it.
Yeah.
Now, doing that 5-step calculation by hand was okay for 5 data points, but for hundreds or thousands.
Oh, absolutely not practical. Thankfully, modern tools have made this trivial.
How so?
Well, take Python again. Its statistics module has a function stdev. You just give it your data, and boom, it calculates the sample standard deviation instantly. Same in Excel, STGEVS, R, SPSS. All statistical software does this easily.
That's a huge time saver. Any particularly interesting modern applications of standard deviation you've come across?
Yeah, loads. In machine learning, it's fundamental for something called feature scaling, specifically z-score normalization.
Z-scores.
Yeah, transforming data, so it has a mean of 0 and a standard deviation of 1. It helps many algorithms perform better by putting all variables on a comparable scale. It's also crucial in anomaly detection. If a data point falls, say, more than 3 standard deviations away from the mean, it's often flagged as a potential outlier or anomaly that needs investigation.
Ah, using that 99.7% rule.
Exactly. And in healthcare, think about quality improvement. Hospitals analyze the standard deviation of things like patient wait times, or length of hospital stays, or infection rates.
Why?
Because high variability often indicates inefficiency or inconsistency in care. The goal is often to reduce the standard deviation, to make processes more reliable and outcomes more predictable.
That makes perfect sense. If the standard deviation of wait times is huge, it means some people breeze through while others wait forever. That's a system problem.
Precisely. Or think about a nursing home. Maybe the average length of stay is 30 days, with a standard deviation of 5 days.
Okay.
That tells us most residents probably stay between 25 and 35 days within 1 SD. If you see someone with a stay less than 20 days, or longer than 40 days, beyond 2 SDs, that's unusual. It might warrant a closer look to understand why their stay was so different.
Right, it flags cases that need attention. Okay, so standard deviation and variance give us this really powerful way to quantify the average spread around the mean. But what if we want to, say, compare different groups? Or see if there are meaningful relationships between different variables?
Ah, right. That moves us beyond just describing the spread within a single data set. Now we're talking about making comparisons and inferences. That's where statistical significance tests and regression analysis come into play.
Okay, let's dive into statistical significance tests first. What are they, broadly speaking, and when would we use them?
Statistical significance tests are tools that help us decide if the differences we observe between groups or the relationships we see between variables are likely to be real, or if they could have just happened by random chance.
So, separating signal from noise.
Pretty much, yeah. They help us assess the evidence against a default assumption called the null hypothesis. The null hypothesis usually states that there's no real difference or no real relationship. The test tells us if our data provides strong enough evidence to reject that null idea.
Okay, give us an example of a common one.
A really common one, especially for categorical data, data that falls into distinct groups or labels, is the chi-square test.
Chi-square, heard of it. What does it do?
It's used to examine whether there's a statistically significant association or relationship between 2 categorical variables.
Like,
Is there a relationship between smoking status, smoker, non-smoker,
yeah,
and developing a certain lung condition, yes, no, or between different teaching methods, method I, method B, and passing rates, pass-fail.
Okay, so how does it figure out if there's a real connection, not just random overlap?
It works by comparing the frequencies you actually observed in your data, the O values, with the frequencies you would expect to see if there was absolutely no relationship between the variables, the E values. These expected values are calculated based on the overall totals.
Comparing observed versus expected.
Right. The chi-square statistic itself is calculated based on the differences between these observed and expected counts across all the categories. The formula is basically summing up observed expected squared divided by expected for all cells in your comparison table.
Okay, a formula exists.
A large chi-square value means there's a big discrepancy between what you saw and what you'd expect by chance alone. This suggests there is likely an association.
And then there's the p-value.
Exactly. We look at the p-value associated with that chi-square statistic. If the p-value is very small conventionally, less than 0.05, we say the result is statistically significant.
Meaning we reject the no relationship idea?
We reject the null hypothesis, yes, and conclude that there probably is a real association between the variables in the larger population.
Can you give us a concrete example, maybe from healthcare again?
Sure. Imagine we're looking at infection rates in two different wings of a long-term care facility over, say, 6 months, Wing A and Wing B. We count how many residents got an infection and how many didn't in each wing.
Okay, comparison table.
We could use a chi-square test to see if the proportion of residents getting infected is significantly different between Wing A and Wing B. Are the observed rates just random fluctuation, or does one wing genuinely have a higher infection rate?
Right.
If we calculate the chi-square statistic and find it's, say, 7.68, and the corresponding p-value is less than 0.01, which is less than 0.05, then we'd conclude there is a statistically significant association between the facility wing and the infection rate. The difference isn't likely just due to chance.
That's a really clear application. Okay, what's another common significance test we might run into?
Another workhorse, especially when comparing the means or averages of two groups on some continuous measurement, is the t-test.
T-test. Okay.
Yep.
Chi-square for categories, t-test for means.
Generally, yes. The t-test helps us determine if the average value of something like blood pressure, test scores, recovery time is significantly different between two distinct groups. For example, a group getting a new drug versus a group getting a placebo.
Like in clinical trials.
Exactly. It assumes the data within each group is roughly normally distributed, though it's somewhat robust to violations of that.
So if we wanted to compare the average recovery time for patients who got that new drug versus patients who got the standard treatment, we could use a t-test.
Perfect example. The t-test calculates a t-statistic. This statistic considers the difference between the two group means, the variability within each group, using their standard deviations or variances, and the number of people in each group.
Okay.
A larger t-statistic generally means a bigger difference between the groups relative to the variation within them. And again, we look at the p-value.
Below 0.05 means significant.
If the p-value is less than 0.05, we typically conclude that the observed difference in average recovery times is statistically significant. It's unlikely to be just a random fluke. The new drug probably does have a different effect than the standard treatment.
How are these tests being used now? Any modern twists?
Well, the main advancement is how easy they are to perform. Software like SPSS, R, and Python's scipy.stats module makes running these tests incredibly efficient.
Just a few clicks or lines of code.
Pretty much. For instance, in Python, you can run that chi-square test using the chi2 contingency function. Super straightforward.
That's handy.
And in machine learning, while maybe not their primary use, these tests sometimes pop up for validating things. Maybe comparing the performance metrics of two different algorithms, using a t-test to see if one is significantly better.
So these tests give us a more rigorous way to compare groups, to see if the differences we're observing in our data are likely real and meaningful, not just chance.
Precisely. They provide a statistical framework for making inferences and drawing conclusions beyond just describing the data.
Okay. And building on that idea of exploring relationships between variables, you mentioned regression analysis.
Yes. Regression analysis takes us a step further. It's not just about if there's a relationship, but about modeling that relationship.
Modeling sounds like predicting things based on data.
That's a big part of it, yeah. Regression analysis is a really powerful statistical technique for modeling the relationship between a dependent variable that's the outcome you're trying to predict or explain,
Okay.
and one or more independent variables. Those are the factors you think might influence or predict that outcome.
So predicting house prices based on square footage or student grades based on study time?
Exactly those kinds of things. We often start with the simplest form, which is linear regression.
Linear, meaning straight line.
Yeah, it assumes a straight line relationship between the variables. As one goes up, the other goes up or down in a consistent linear way.
And how do we measure how strong that linear relationship is? I think I've heard of the correlation coefficient.
Yes, spot on.
Ah.
The correlation coefficient, usually written as R, measures the strength and direction of a linear relationship between two variables.
Strength and direction.
It ranges from -1 to +1. A correlation near +1 means a strong positive linear relationship. As x goes up, y goes up predictably. Near -1 means a strong negative linear relationship. As x goes up, y goes down predictably.
And near zero.
Near zero means there's little to no linear relationship. Important caveat. It might still have a nonlinear relationship, like a curve, but R only measures the straight line part.
Got it. So regression analysis then builds a model to actually describe this relationship mathematically. Find the best line.
Exactly. In simple linear regression, one independent variable, we aim to find the equation of the best fitting straight line through our data points. It minimizes the overall distance between the line and the actual data points.
And that equation has a slope and an intercept.
Yep, the formula is typically written as y0 plus 1x plus r.
Whoa, Greek letters.
Hell yeah, beta 0 is the intercept where the line crosses the y-axis, the predictive value of y when x is 0. Beta 1 is the slope, how much y is predicted to change for every 1 unit increase in x.
And the epsilon.
That's the error term. It represents the difference between the actual y value for a data point and the y value predicted by the line. Regression doesn't usually predict perfectly, so there's always some error or residual.
Okay, finding the best line through the data. What about more advanced stuff or modern applications?
Oh, regression is a massive field. Simple linear regression is just the start. If you have multiple independent variables predicting y, like predicting house price using square footage, number of bedrooms, and location, that's multiple linear regression.
Makes sense.
If the relationship is in a straight line, you might use polynomial regression, fitting curves, or other nonlinear models. And when you have tons of potential predictors, there are techniques like regularized regression. Lasso and ridge are common names that help select the most important variables and prevent the model from becoming too complex and overfitting the data.
Overfitting, like it learns the noise, not just the signal.
Exactly. And again, software makes this accessible. Python's scikit-learn library is hugely popular for all sorts of regression. You can fit a model, get the slope, coefficient, and intercept, and make predictions with just a few lines of code.
Can you give us a quick code example snippet?
Sure. In scikit-learn, it might look something like from slurn.linear model, import linear regression, then you create a model linear regression. You train it on your data.model.fit, xy, where x is your independent variable, sy is your dependent variable. Then you can print the results, print fslope.model.cafe intercept.crow model.intercept.
Cool. And a practical example, maybe back in healthcare.
Absolutely. Regression is used extensively. For instance, predicting a patient's risk of hospital readmission.
Ah, that's a big one for hospitals.
Yeah, they might build a model using patient characteristics, age, previous admissions, specific diagnoses, maybe social factors, and details from their initial hospital stay to predict the likelihood they'll need to come back soon after discharge.
And that helps them target interventions.
Exactly. Identify high-risk patients and maybe provide extra support, follow-up calls, or care coordination to try and prevent that readmission. It's also used to predict disease risk, model treatment effectiveness, forecast resource needs, tons of applications.
It's really fascinating how these statistical tools, starting from just calculating a simple range, build up to these powerful predictive models with such concrete, important applications.
That's precisely why understanding these concepts, even at a high level, is so valuable. They really do provide a fundamental framework for making sense of the complex, data-filled world around us.
Well, we've certainly covered a lot of ground today in this deep dive into statistical measures of data dispersion.
We really have.
We started with the simplicity, maybe deceptive simplicity of the range.
Quick look.
Then explored frequency distributions to actually visualize the shape and patterns in our data.
Seeing the hills and valleys.
We quantified that average spread around the mean using standard deviation and variance, the real workhorses.
Getting precise about the wobble.
And finally, we touched on how statistical significance tests like chi-square and t-tests help us compare groups rigorously, and how regression analysis lets us model relationships between variables.
And the key takeaway through all of this, I think, is that understanding the spread of data using whichever of these tools is appropriate gives you a much more complete, much more insightful picture than just looking at a simple average.
Right. It's not just about the center, it's about the whole distribution.
It lets you assess consistency, spot potential issues or outliers, judge reliability, and ultimately make more informed decisions, whether that's in your job, your health, or just understanding news reports.
Absolutely. So for you, the listener, we really hope this deep dive has given you some valuable insights. Why understanding how data is distributed, how spread out it is just so critical in so many different fields.
It's about looking beyond that single summary number.
Yeah, and truly understanding the variability, the shape, the relationships within the information you encounter.
Which brings us, I suppose, to a final thought for you to maybe ponder on your own. And now that you have a better handle on these different ways to measure and think about the spread of data, how will you approach the statistics you come across from now on? In your daily life, in your work?
Mm. What new questions might pop into your head?
Exactly. What new questions will you start asking when someone just gives you an average? Consider how this knowledge, this awareness of dispersion, might empower you to make slightly better, more informed decisions.
Whether that's about personal finances or health choices or just interpreting some study you read about.
Yeah, we'd really encourage you to explore how these concepts, range, frequency, standard deviation, significance, regression, are actually applied in the fields that genuinely pique your curiosity. You'll start seeing them everywhere.